In statistics, the p-value is a function of the observed sample results that is used for testing a statistical hypothesis. More specifically, the p-value is defined as the probability of obtaining a result equal to or more extreme than what was actually observed, assuming that the null hypothesis is true. Here, more extreme is dependent on the way the hypothesis is tested. Before the test is performed, a threshold value is chosen, called the significance level of the test, traditionally 5% or 1% and denoted as alpha. If the p-value is less than or equal to the chosen significance level, the test suggests that the observed data are inconsistent with the null hypothesis, so the null hypothesis must be rejected. However, that does not prove that the tested hypothesis is true. When the p-value is calculated correctly, this test guarantees that the type 1 error rate is at most alpha. Since p-value is used in frequentist inference, it does not in itself support reasoning about the probabilities of hypotheses but is only as a tool for deciding whether to reject the null hypothesis. Statistical hypothesis tests making use of p-values are commonly used in many fields of science and social sciences, such as economics, psychology, biology, criminal justice and criminology, and sociology. Misuse of this tool continues to be the subject of criticism. Basic concepts. The p-value is used in the context of null hypothesis testing in order to quantify the idea of statistical significance of evidence. Null hypothesis testing is a reductio ad absurdum argument adapted to statistics. In essence, a claim is shown to be valid by demonstrating the improbability of the consequence that results from assuming the counterclaim to be true. As such, the only hypothesis that needs to be specified in this test and which embodies the counterclaim is referred to as the null hypothesis. A result is said to be statistically significant if it can enable the rejection of the null hypothesis. The rejection of the null hypothesis implies that the correct hypothesis lies in the logical complement of the null hypothesis. However, unless there is a single alternative to the null hypothesis, the rejection of null hypothesis does not tell us which of the alternatives might be the correct one. For instance, if the null hypothesis is assumed to be a standard normal distribution n, the rejection of this null hypothesis can either mean the mean is not zero, or the variance is not unity, or the distribution is not normal, depending on the type of test performed. However, supposing we manage to reject the zero mean hypothesis, the null hypothesis test does not tell us which non-zero value we should adopt as the new mean. In statistics, a statistical hypothesis refers to a probability distribution that is assumed to govern the observed data. If is a random variable representing the observed data and as the statistical hypothesis under consideration, then the notion of statistical significance can be naively quantified by the conditional probability, which gives the likelihood of the observation if the hypothesis is assumed to be correct. However, if is a continuous random variable and an instance is observed thus, this naive definition is inadequate and needs to be changed so as to accommodate the continuous random variables. Nonetheless, it helps to clarify that p-values should not be confused with probability on hypothesis such as the probability of the hypothesis given the data, or the probability of the hypothesis being true, or the probability of observing the given data. Definition and interpretation. The p-value is defined as the probability, under the assumption of hypothesis, of obtaining a result equal to or more extreme than what was actually observed. Depending on how it is looked at, the more extreme than what was actually observed can mean or the smaller of an. Thus, the p-value is given by for right tail event, for left tail event, for double tail event. The smaller the p-value, the larger the significance because it tells the investigator that the hypothesis under consideration may not adequately explain the observation. The hypothesis is rejected if any of these probabilities is less than or equal to a small, fixed but arbitrarily predefined threshold value, which is referred to as the level of significance. Unlike the p-value, the level is not derived from any observational data and does not depend on the underlying hypothesis. The value of is instead determined by the consensus of the research community that the investigator is working in. Since the value of that defines the left tail or right tail event is a random variable, this makes the p-value a function of a random variable in itself defined uniformly over interval, assuming is continuous. Thus, the p-value is not fixed. This implies that p-value cannot be given a frequency counting interpretation since the probability has to be fixed for the frequency counting interpretation to hold. In other words, if the same test is repeated independently bearing upon the same overall null hypothesis, it will yield different p-values at every repetition. Nevertheless, these different p-values can be combined using Fisher's combined probability test. It should further be noted that an instantiation of this random p-value can still be given a frequency counting interpretation with respect to the number of observations taken during a given test. As per the definition, as the percentage of observations more extreme than the one observed under the assumption that the null hypothesis is true. The fixed predefined level can be interpreted as the rate of falsely rejecting the null hypothesis, since this also means that if we fix an instantiation of p-value and allow to vary over, we can obtain an equivalent interpretation of p-value in terms of level as the lowest value of that can be assumed for which the null hypothesis can be rejected for a given set of observations. Obviously, assuming n smaller than the instantiated p-value will end up not rejecting the null hypothesis. Calculation. Usually, instead of the actual observations, is instead a test statistic. A test statistic is a scalar function of all the observations, such as the average or the correlation coefficient, which summarizes the characteristics of the data by a single number, relevant to a particular inquiry. As such, the test statistic follows a distribution determined by the function used to define that test statistic and the distribution of the input observational data. For the important case in which the data are hypothesized to follow the normal distribution, depending on the nature of the test statistic and thus the underlying hypothesis of the test statistic, different null hypothesis tests have been developed. Some such tests are Z-test for normal distribution, T-test for students T-distribution, F-test for F-distribution. When the data do not follow a normal distribution, it can still be possible to approximate the distribution of these test statistics by a normal distribution by invoking the central limit theorem for large samples, as in the case of Pearson's chi-squared test. Thus, computing a p-value requires a null hypothesis, a test statistic, and data. Even though computing the test statistic on given data may be easy, computing the sampling distribution under the null hypothesis, and then computing its cumulative distribution function is often a difficult computation. Today, this computation is done using statistical software, often via numeric methods, but in the early and mid-20th century, this was instead done via tables of values, and one interpolated or extrapolated p-values from these discrete values. Rather than using a table of p-values, Fisher instead inverted the CDF, publishing a list of values of the test statistic for given fixed p-values. This corresponds to computing the quantile function. Examples. Here a few simple examples follow, each illustrating a potential pitfall. One roll of a pair of dice. Suppose a researcher rolls a pair of dice once and assumes a null hypothesis that the dice are fair, not loaded or weighted toward any specific number. Roll. Result, uniform. The test statistic is the sum of the rolled numbers, and is one-tailed. The researcher rolls the dice and observes that both dice show 6, yielding a test statistic of 12. The p-value of this outcome is 1/36 or about 0.028. if the researcher assumed a significance level of 0.05. This result would be deemed significant and the hypothesis that the dice are fair would be rejected. In this case, a single roll provides a very weak basis to draw a meaningful conclusion about the dice. This illustrates the danger with blindly applying p-value without considering the experiment design. 5 heads in a row. Suppose a researcher flips a coin 5 times in a row and assumes a null hypothesis that the coin is fair. The test statistic of total number of heads can be one-tailed or two-tailed. A one-tailed test corresponds to seeing if the coin is biased towards heads, but a two-tailed test corresponds to seeing if the coin is biased either way. The researcher flips the coin 5 times and observes heads each time, yielding a test statistic of 5. In a one-tailed test, this is the most extreme value out of all possible outcomes, and yields a p-value of 5 equals 1/32, 0.03. If the researcher assumed a significance level of 0.05, this result would be deemed significant and the hypothesis that the coin is fair would be rejected. In a two-tailed test, a test statistic of 0 heads is just as extreme, and thus the data of HHHHH would yield a p-value of 2 times 5 equals 1/16, 0.06. which is not significant at the 0.05 level. This demonstrates that specifying the direction halves the p-value and can mean the difference between data being considered significant or not. Sample size dependence. Suppose a researcher flips a coin some arbitrary number of times and assumes a null hypothesis that the coin is fair. The test statistic is the total number of heads and is a two-tailed test. Suppose the researcher observes heads for each flip, yielding a test statistic of n and a p-value of 2/2 n. If the coin was flipped only 5 times, the p-value would be 2/32 equals 0.0625, which is not significant at the 0.05 level. But if the coin was flipped 10 times, the p-value would be 2/1024, 0.002, which is significant at the 0.05 level. In both cases, the data suggest that the null hypothesis is false, but changing the sample size changes the p-value. In the first case, the sample size is not large enough to allow the null hypothesis to be rejected at the 0.05 level. This demonstrates that in interpreting p-values, one must also know the sample size, which complicates the analysis. Alternating coin flips. Suppose a researcher flips a coin 10 times and assumes a null hypothesis that the coin is fair. The test statistic is the total number of heads and is two-tailed. Suppose the researcher observes alternating heads and tails with every flip. This yields a test statistic of 5 and a p-value of 1, as that is the expected number of heads. Suppose instead that the test statistic for this experiment was the number of alternations, which is again two-tailed. That would yield a test statistic of 9, which is extreme and has a p-value of. That would be considered extremely significant, well beyond the 0.05 level. These data indicate that, in terms of one test statistic, the dataset is extremely unlikely to have occurred by chance. But it does not suggest that the coin is biased towards heads or tails. By the first test statistic, the data yield a high p-value, suggesting that the number of heads observed is not unlikely. By the second test statistic, the data yield a low p-value, suggesting that the pattern of flips observed is very, very unlikely. There is no alternative hypothesis, and such data could have many causes. The data may instead be forged, or the coin may be flipped by a magician who intentionally alternated outcomes. This example demonstrates that the p-value depends completely on the test statistic used and illustrates that p-values can only help researchers to reject a null hypothesis, not consider other hypotheses. Impossible outcome and very unlikely outcome. Suppose a researcher flips a coin 2 times and assumes a null hypothesis that the coin is unfair. Both sides are heads. The test statistic is the total number of heads. The researcher observes one head and one tail, yielding a test statistic of 1 and a p-value of 0. In this case, the data is inconsistent with the hypothesis. For a two-headed coin, the tail can never come up. In that case, the outcome is not simply unlikely in the null hypothesis but in fact impossible, and the null hypothesis can be definitely rejected as false. In practice, such experiments almost never occur, as all data that could be observed would be possible in the null hypothesis. If the null hypothesis were instead that the coin came up heads 99% of the time, the p-value would instead be in that case. The null hypothesis could not definitely be ruled out, but the null hypothesis would be rejected at the 0.05 level since the outcome is less than 2% likely in the null hypothesis. Coin flipping is an example of a statistical test. An experiment is performed to determine whether a coin flip is fair or unfairly biased. Suppose that the experimental results show the coin turning up heads 14 times out of 20 total flips. The null hypothesis is that the coin is fair, and the test statistic is the number of heads. If a right-tailed test is considered, the p-value of this result is the chance of a fair coin landing on heads at least 14 times out of 20 flips. That probability can be computed from binomial coefficients, as this probability is the p-value, considering only extreme results that favor heads. This is called a one-tailed test. However, the deviation can be in either direction, favoring either heads or tails. The two-tailed p-value, which considers deviations favoring either heads or tails, may instead be calculated. As the binomial distribution is symmetrical for a fair coin, the two-sided p-value is simply twice the above calculated single-sided p-value. The two-sided p-value is 0.115. In the above example, null hypothesis, the coin is fair, with prob equals 0.5. Test statistic, number of heads, level of significance, 0.05. Observation O, 14 heads out of 20 flips, and two-tailed p-value of observation O given h0 equals 2 asterisk min, prob equals 2 asterisk min equals 2 asterisk 0.05 at equals 0.115. Note that the prob equals 1 prob plus prob equals 1 0.058 plus 0.036 equals 0.978. However, symmetry of the binomial distribution makes that an unnecessary computation to find the smaller of the two probabilities. Here, the calculated p-value exceeds 0.05, so the observation is consistent with the null hypothesis, as it falls within the range of what would happen 95% of the time where the coin is in fact fair. Hence, the null hypothesis at the 5% level is not rejected. Although the coin did not fall evenly, the deviation from expected outcome is small enough to be consistent with chance. However, had one more head been obtained, the resulting p-value would have been 0.0414. The null hypothesis is rejected when a 5% cutoff is used.